then he defined G1U as the potential energy, but I guess this is the action.
Yeah. The action is the sum of J0 plus J1.
F Ux
Sum of the difference.
ut.
What did you say?
The sum of the difference.
Oh, the difference, kinetic minus potential. Right, that's the difference.
But what I was saying is that this is the, well,
Mhm.
I have this one, but this is the sum of these over 0 to T0 to T1. Or this, here. And then he used the stationary condition from Hamilton's principle, which says that the change of the energy is conserved. Change of it doesn't change.
J0 or J1?
The energy is conserved. Difference of G0 and G1.
Difference is the action, okay.
So actually it says that for a small perturbation, G0 and G1 for U plus SV, and here V is also from RK and S is our perturbation coefficient. And he says S is equal to 0 for our perturbation. It's equal to 0.
So that's the principle of least action, if you want, on stationary action. So that quantity J0 minus J1, as John mentioned, that's called the action. And these are basically the Lagrangians. I mean, the UT squared minus F of U, and that's the Lagrangian. The action is always an integral of the Lagrangian.
And now we used G0 U plus SV because SV from here it's going to be this one should be UT plus SVT. And then we calculated this as the this one should be equals to
You write V as U. That another one is V, right?
This is UT, VT, yeah.
That's the second is V, not U. It looks like U.
Oh, he's doing a script V.
What?
He's doing a script V.
Oh yeah, but it's still a V. Is that way how to compute it? You just substitute there U plus SV and you compute it, and then you just pick the linear term in V. That's all.
And then using integration by parts, I'll shift this derivative on V onto UT, and then it equals to the negative some region.
What he's doing is called the variational derivative.
TT, and V, this is G0, like he calculated, and then for the G1, you've got the dash. This is equal to 0, not the same way.
Has anybody taken variational calculus? Have you seen
So it's really
it? What?
It's been a while.
Because that's exactly what he's doing.
And then this.
Let me say one word here, because that's just, we are learning something. So suppose that you have some function of S, okay? So then what do? You want to compute so-called variational derivative. What is variational derivative? Well, it's like like usual derivative but an infinite dimension. So what is it? You take this S and you add, well, as you said, S, well, that S is a different, let me call it epsilon, V, okay, and then you expand this in like power series in epsilon. And so you'll get S of U plus linear term in epsilon plus something here, well, let me call it that difference in U and V, and that is linear in V. And then you get, the rest will be of order epsilon squared, that you can forget, right? So this is a linear in V. Well, it's a non-linear in U, but linear in V. Therefore, this guy looks like some operator acting on V. And this operator is that derivative, variational derivative. So usually, if this is an integral of some other, like local Lagrange, if this is local functional, local means the integral of something, then this will be an integral and then, well, of something, and then you'll get something here, and then V. Well, when you do this calculation, you'll get a bunch of derivatives on V, and then by integration by parts, you bring all of them to that, okay? And of course, when doing that, you have to use boundary conditions. And the boundary conditions should be such that all these self-boundary terms cancel, because otherwise this is not defined. He didn't mention that, but when he did that, integration by part over T, because he must use the boundary conditions, that thing vanishes, and therefore the derivative just goes to that. And then, well, then this is exactly this variational derivative. And of course you can write this as d by the epsilon of S of U plus epsilon V and epsilon equal to 0. Well, this doesn't depend on epsilon, these are higher orders. So it's exactly this quantity, d by the epsilon at epsilon equal to 0, picks that linear coefficient. If you want, you could do that derivative, or you could just expand and look at the linear coefficient. And when you do that, well, this is a function, so it depends on x, right? And so well, it could be a function, a vector, whatever, tensor. But then you bring all derivatives of that, and whatever is here, that is the variational derivative. And that's exactly what it is done, okay? But again, it needs to use boundary condition, and if it was such that we guarantee that those terms vanish.
And also the same,